Yes, sir.
Okay. So have you gone through the lectures of week 5? No one. So how many lectures have you seen? Or have you watched all the weeks, 1 week, second, third, fourth, fifth? Because it's week 5. So around, I think 20 lectures should be there. Suraj Kishore is saying yes. Okay. So no one has gone through the lectures, right? Except Suraj. Okay, it's fine. We can start now. So today we are gonna start week 5 assignment. Course you must know physics of renewable energy systems taken by Professor Amrish Chandra. Even you must have received an email regarding that online or interaction with Professor Amrish Chandra on I think 2nd September, right? Have you seen or have you received any email? Yes, no. Only Suraj Kishore has received. Be responsive. Sri Haran Rajkumar saying yes. Okay. If you can't speak, just write in the chat box. Otherwise, you can speak. So, you must know me. I'm Ravi Kumar from IIT Bombay. I'm pursuing my PhD in the field of renewable energy only. So, let's start our discussion. So, this is the first question, which says, which of the following can be taken as a form of external energy? Anyone here know what is external energy and what is internal energy? Okay, let me show the options. These are the options: chemical energy, thermal energy, electrical energy, or none of these. So you just need to tell me which of the following is a form of external energy. Raja saying chemical. Okay. See, there is no harm in giving any answer. If you know, it's okay. If you don't know, it's fine. Nothing will change. Suraj saying D. Okay. Divya HD. Okay. Okay, just now let me know what is internal energy and what is external energy. Don't give me any definition, just tell me one example of internal energy and one example of external energy. See, if you are saying none of these, and right, this is the answer. Okay, so these are the example of external energy. What about internal energy? Oh, sorry, these are not the example of external energy. These are internal energy. Fine. So example of internal energy is chemical energy, thermal energy, or electrical energy. Now let me know the example of external energy. Biomass. It's fine, Suraj, but biomass is not the answer. Means you have not gone through the lectures. This is a chart, energy stored in matter. So transferred by work action, the energy which is transferred by work action is known as external energy, and which is kinetic energy and potential energy. While on the other hand, the energy which is transferred by work, heat, or convection, that energy is known as internal energy. And the example of this internal energy is chemical, nuclear, electrical, magnetic, internal mechanical, or thermal and bond. Like, so the example of internal energy will be potential energy or kinetic energy. So answer of this question will be D, because neither of these are the example of external energy. I think it is fine now. This is from the week 5 lecture 1 only. Okay. So let's move to the next question. So second question says, what are the advantages or uses of the energy storage technology? You just need to tell me the advantages of energy storage technologies. These are the options. First says ensuring continuity. Second says mobile technologies. Third says off-grid application. And like fourth option says all of the above. I am asking advantages of energy storage technologies. Suraj, all of the above. Great. Deepa, right? D. Okay, the answer is all of the above. But how? Let's see. Ensuring continuity. If we have solar energy, so we will get it in the time of daytime only. So for continuity or to be used in evening or in night, what we need? Storage. What we do generally? We store it in batteries. So first advantage of energy storage technology will be ensuring continuity. Second says mobile technologies. I think you must have mobile, laptop, wearables, watches. So these all are running on the batteries. So battery is an example of energy storage technology. So yes, second option is also correct. Third option says off-grid applications. Means it is working even grid is not available. Off-grid application like electric vehicle EV. We are not connecting the wire to the pole, electricity pole. So it is off-grid. Yes, then option C is also correct. Then the answer of this question is D, all of the above. Here this image is from the lecture only. So it says ensure continuity, restrict wastage, mobile technologies, e-vehicles, bring balance between supply and demand, off-grid application, and ensure availability as per the need. So these three are here, 1, 2 and 3. I think it is fine. Yes, no, need more explanation. Okay, it's very easy, it's fine. Okay, Suraj. Okay, thank you, Suraj. So let's move to the next question. That says, what are the main disadvantages of compressed air based energy storage? So first let me tell you, compressed air is a way of storing energy. What we do? We just store compressed air below the ground. So this is a way of storing energy. So you just need to tell me the disadvantages due to this kind of storage technology. These are the options in front of you. First says contamination of water. Second says storing of small amount of energy. Third says requirement of special geological formation. And D, last option says high maintenance cost. What are the disadvantages of using compressed air as a method for energy storage? Yes, Kishore, Suraj Kishore is saying option C. Okay. Here it may be two options which are correct. So Suraj is saying C. C is absolutely correct. Okay, Fatima is right. Suraj saying A, contamination of water. Right. Absolutely correct. Because we are storing this energy below the ground. So there will be groundwater. And heating of groundwater is also a kind of contamination of water. Because if air will be compressed, it will generate heat. So contamination of water will take place, and also requirement for special geological formation. Why? Because if we are compressing air here and it is producing heat, so here it may be coal present, and this coal may be burned due to this heat. That's why requirement of special geological formation is necessary. Right. This is from the lecture only. Disadvantages: contamination of water, spontaneous combustion of coal. So yes, A and C are the correct answer. Okay, let's move to the next question. That says flywheel for energy storage generally spins at. Do you know what is a flywheel? Anybody? Do you know? Yes, no, maybe, may not. Okay, let me tell you. Flywheel is a way of energy storing technology. What we do, we, like, this is a box here, and here is a wheel of higher mass, and this is a shaft, and inside this box is vacuum. So what we are doing, we are, like, if we have some kind of energy, like electricity is there, solar PV is producing electricity, what we will do, we will just attach a motor. This is motor or generator. So during the daytime or during the excess energy production, what will happen, this motor will rotate this flywheel. And due to vacuum here, it won't stop due to friction or any kind of resistance, because there is no air. So it will be continue in motion. And if there is no electricity, then what we can do, using this kinetic energy, we can generate electricity by a generator. So first a motor is moving this flywheel. So motor is producing kinetic energy, and after some time this kinetic energy we are converting it into back electricity. So back into electricity we are converting it. So you just need to tell me the RPM of flywheel. Do you know what is RPM? RPM means nobody knows. What should be an RPM? If a wheel is rotating, then what does it mean RPM? Rotation per minute. Raja Sekhar, absolutely right. Kokila Vani, right. Rotation per minute. So I think now question is clear. Now you can tell me the RPM of a flywheel. Will it be less than 10,000, between 10 to 25,000, between 25 to 50,000, or more than 50,000? As nobody have gone through the lectures, so Suraj saying sad C. Okay, Suraj, you are absolutely right. Yes, 25 to 50,000 is the answer. Great. Flywheel for energy storage typically spin at 25 to 50,000 RPM. So answer is C. Now I think you have understood what is this flywheel storage technology. You just need to tell me the principle behind this storage technology. The principle. Okay, what is the first law of motion? Yes, someone is speaking. Speak, please. First law of motion. Inertia. Yes, Raja. It's inertia. Mechanical inertia is the basis of this storage system. Yes. I think inertia everyone knows. Okay. It's clear. Let's move to the next question. So it says the application of compressed air energy storage, which I told you before 2 slides only. What is this compressed air energy storage system? So you just need to tell me the application. These are the options where this compressed air energy storage system can be used. Can it be used in power generation? Yes or no? A and B. Okay. Shura is saying A and B. What about others? Okay, I am assuming Suraj is right. Then tell me why not C? Do you know what is UPS? What is UPS? Fatima is saying B. Okay. Fatima, A and B are right. Raja saying uninterrupted power supply. Great. So UPS is uninterrupted power supply. But why we can't use compressed air energy storage for UPS purpose? Because switching time. Switching time for this technology is more. And in case of UPS, it should be in milliseconds. I think now everything is clear. Why not UPS? Yes, the answer will be A and B, both aerospace and power generation. Okay, let's move to the next question. Which of the following has highest round trip efficiency? Highest round trip efficiency. What is round trip efficiency? See, if I am asking some question or if some word is there in the question and if you don't know the meaning, then you can't answer it. So if you are not understanding the question, you can ask. I will tell you. See, I'm telling you one thing. Let's assume this is a energy storage device and we are storing energy P input, and after some time we are using this energy as P output. This is our storage. So here efficiency will be, round trip efficiency will be P out divided by P in. I think now it is fine. Okay, so these are the options: supercapacitor, lead acid battery, hydrogen gas storage, or flywheels. Among these four, which one will have highest round trip efficiency? Round trip efficiency is defined as the power we are storing or energy we are storing and power or energy we are using after some time. Suraj saying flywheel. Tami Jahan saying flywheel. Okay. So two students are saying flywheels. Three. Raja is saying lead acid battery. One student is saying lead acid battery. What about others? Pavan Krishna saying C, hydrogen gas storage. Okay. Salini going with the D. Deepa going with the C. Fatima is also with the C. It's going to be very interesting. One more for C. Okay, let me tell you, nobody is correct here. Neither option B is correct, no C nor D. It means you don't know what is a supercapacitor. Just go and read about supercapacitors. Why so many researchers are working on supercapacitors? Okay. Yeah, zero resistance and these things will come from superconductor only. But we currently don't have any superconductor at room temperature. Yes, Salini, you are saying somewhat correct. Zero resistance, high storage capacity, more round trip efficiency. But this word zero resistance is associated with superconductors. Yes. So this is the table from the lecture only. You can see round trip efficiency is given here, and round trip efficiency for supercapacitor or superconducting magnets are 95%. So highest round trip efficiency is for supercapacitor. So the correct answer is A. Let's move to the next question. Find the amount of illumination in 1.5 sun. This illumination unit is kilowatt per meter square. So options are 0.5 kilowatt, 1 kilowatt, 1.5 or 3. You just need to tell me the amount of illumination in 1.5 sun. A, B, C or D? Okay. Two students, Pavan and Arvind ji, saying option A, 0.5. Gayatri is saying option C. Tami Jahan option A. Okay, let's solve it right now. One sun equals to, do you know how many kilowatt per meter square? One student saying B, Suraj. Oh, Suraj saying B. Do you know 1 sun equals to how many kilowatt per meter square? Sir, the answer is C. Tamijan saying C. Yes, Tamijan, you are absolutely right. Answer is C. Because 1 sun equals to 1 kilowatt hour, and then 1.5 sun will be 1.5 kilowatt per meter square. So yes, you can see 1 sun equals to 1 kilowatt per meter square, and M into 1 kilowatt is, or M here is 1.5. Yes, the answer is C. So correct answer is C. Great, Tamijan, you are right. So let's move to the next question, which says mechanical energy storage is in the form of. So the mechanical storage is in the form of kinetic energy only, potential energy only, in both, or none. Arvind, C. Yes, Arvind, you are right. The option is C. Yes, Gayatri, answer is right. C. Mechanical will have both kind of energy, kinetic plus potential. Okay, so for this kinetic energy, you have seen an example. What is that? Name it. We were discussing just few minutes ago. Turbine engine. Turbine engine is energy storage technology. Really? What is this turbine engine? What you want to say? It's kinetic potential. Yes, Gayatri, flywheel. Flywheel is a form of, is a kind of technology. And for this potential energy, for this potential energy, it's something related to, like Arvind is saying, turbine engine. It's kind of hydropower. Like we are, if this is an height h, and there are some water here, and this is a reservoir at a height h. So what we will do, we will pump it, this water, at somewhat height, so it will have some kind of potential energy, mgh, this potential energy. So what we have done, we have stored electricity in the form of potential energy. So potential energy is a form of mechanical energy. So after the unavailability of this electricity, what we can do, we will just open this reservoir, and here we will use our generator, and it will generate electricity back. So that is an example of potential energy. Yeah, option C, right. So let's move to the next question, which is second last question for today, and this question is very easy. You just need to match these. So isothermal process will have constant volume, pressure, temperature. What it will have? Similar case for adiabatic, isobaric, isochoric. It's very easy. Okay, Kokila saying constant temperature, isothermal. Isothermal is here, constant temperature, yes. So according to her, A is third. Constant pressure is isobaric. Isobaric is constant pressure. So C goes to second. What about others? What about isochoric? D, V, adiabatic 1. No. What is this 1? I'm not understanding. Tamijan is saying only 1. So this 1 is for isochoric or adiabatic? Adiabatic no heat transfer. Yes. Yes. So B to the 4 and D to the first. D constant volume. Yes. So I think we have done all the 4. Yes. So here also you can see isobaric, isochoric, isothermal, adiabatic. Here pressure is constant for isobaric, isochoric volume is constant, for isothermal temperature is constant, and for adiabatic there is no heat transfer. So now this is the last question for today. So this is a numerical which you need to solve right now. This numerical is very easy to solve. So question 10 says a Carnot engine has an efficiency of 30%. Its efficiency is to be increased to 50. Means it was having 30% efficiency which has been increased to 50%. So to increase this efficiency, what must the temperature of source to be increased if the sink is at 300 Kelvin? You just need to tell me if sink temperature is 300 Kelvin constant. You just need to tell me what should be delta T source. If not understood, let me know. In simple language, I can say if a Carnot engine was having 30% efficiency with sink temperature 300 Kelvin. Now we need to change the temperature of source. For what? To increase this efficiency from 30 to 50. You just need to find out how much temperature we need to increase in the source temperature. Increase in the source temperature you need to find out. If you want formula, I can write it right now, but you need to solve it. You want me to write or yes, no? Do you know the formula for Carnot efficiency? Okay, these options let me show. These are the options. Okay, let me show you the formula as well. So efficiency is can be given as eta 1 minus T sink divided by T source. Now you can solve it. Still I have any doubt, any problem, you can ask, you can write in the chat box. You if you not, then please solve it. Nobody is responding. Are you solving it or not? If not, I can solve it easily. But I want you to work on it. Am I audible to you? Am I connected to the internet? Yes, no? Okay. I felt I got disconnected because no one was responding. Option C. Raja is saying option C. Okay, let me do it because time is going. So if eta is 30% and T sink, temperature of sink is 300 Kelvin, then just find the temperature of source. So using this formula, just putting the value of T sink and efficiency, you will find out T source is 428.6 Kelvin. Now the question says efficiency has been changed to 50%. So now just use this formula again with for the 50%. 0.5, same formula. Just change the efficiency from 30 to 50%. Now you are getting T source is 600 Kelvin. So you have to increase this T source from 428 to 600. And here I am asking delta T only. So it will be 600 minus 428.6 K. How much? Please just tell me the difference. Yeah, A. Yes. So temperature difference is 171.4 Kelvin. So correct answer is A. So we are done with today's lecture. If you have any doubt, you can ask, or I am uploading these videos on YouTube. I am sending link once again. If you have any doubt, you can write in the comment. I will respond there. So let's disconnect. Thanks for attending. I just want to request you, please be responsive. As much as you will be responsive, these classes will be very interesting and you will learn a lot. You are welcome. Okay, bye bye, see you. Kavita, class has been ended, so I am disconnecting. You are very late. Class was from 6 to 7, not from 7 to 8. It's fine. I am uploading these videos on YouTube. You can go through it. It's fine. Chalo, bye.